behind the concept of an E field is that you bring any charge at that location and you know what force acts at that point on that charge. If we try to be a little bit more quantitative, suppose I had here a charge +3. And here I had a charge -1. Here is -1. And I want to know what the field configuration is as a result of these two charges. So you can go to any particular point. You get an E vector which is going away from the +3. You get one that goes to -1, and you have to vectorially add the two. If you're very close to -1, it's very clear because of the inverse R² relationship that the -1 is probably going to win. Let's, in our mind, take a plus test charge now. And we put a plus test charge very close to -1. Say we put it here. Even though +3 is trying to push it out, clearly -1 is most likely to win. And so there will probably be a force on my test charge in this direction. The net result of the effects of the two. Suppose I take the same positive test charge and I put it here, very far away, much farther away than this separation. What do you think now is the direction of the force on my plus charge? Very far away. Excuse me? Why do you think it's to the left? Do you think -1 wins? So you really think the -1 is stronger than the +3 because the +3 would push it out and the -1 tries to lure it in, right? If the test charge is positive. Imagine you all the way to Mass Avenue. You think that this distance matters? Who thinks the force is in this direction? Who thinks it's in this direction? Very good. You've helped them, really. The force is obviously in that direction because if you're very far away, the field will be the same as if you just had a +3 and a -1 somewhere here, which is +2. So if you're far away from a configuration like this, even if you're here, or if you're there, or if you're way there, clearly the field is like a +2 charge and falls off as 1/r². So therefore, if you're far away, the force is in this direction. And now look what is very interesting. Here, if you're close to the -1, the force is in this direction. Here, when you're very far away, maybe I should be all the way here, it's in that direction. So that means there must be somewhere here a point where the E field is 0. Because if the force is here in this direction, it ultimately turns over in that direction, there must be somewhere a point where E is 0, and that is part of your assignment. I want you to find that point for a particular charge configuration. So let's now go to some graphical representations of a situation which is actually +3, -1. Try to improve on the light situation. And let's see how these electric vectors, how they show up in the vicinity of these two charges. So here you see the +3 and the -1, relative units. And let's take a look at this in some detail. First of all, the length of the arrows again indicates the strength. It gives you a feeling for the strength. It's not very quantitative, of course. And so let's first look at the +3, which is very powerful. You see that these arrows all go away from the +3, and when you're closer to the +3, they are stronger, which is a representation of the inverse R² field. If you're very close to the -1, the arrows are pointing in towards the -1, because the 1/r², the -1 wins. And so you see they're clearly going into the direction of the -1. Well, if you're in between the plus and the minus on this line, always the E field will be pointing from the plus to the minus, because the plus is pushing out and the minus is sucking in, so the two support each other. But now if you go very far away from this charge configuration, anywhere, but very far away, much farther than the distance between the two charges, so somewhere here, or somewhere there, or somewhere there, or here, notice that always the arrows are pointing away. And the reason is that +3 and -1 is as good as a +2 if you're very, very far away. But of course, when you're very close in, then the field configuration can be very, very complicated. But you see very clearly that these arrows are all pointing outwards. None of them come back to the -1. None of them point to the -1 direction. And that's because the +3 is more powerful, and then there is here this point, and only one point whereby the electric field is 0. If you put a positive test charge here, the minus will attract it, the plus will repel it, and therefore there comes a point where the two cancel each other exactly. Now there is another way of electric field representation which is more organized, and we call these field lines. So you see again the +3, and you see there the -1. If I release right here, or I place here, a positive test charge, all I know is that the force will be tangential to the field lines. That is the meaning of these lines. So if I'm here, the force will be in this direction. If I put a positive test charge here, the force will be in this direction. And of course, if it's a negative charge, the force flips over. So the meaning of the field lines are that it always tells you in which direction a charge experiences a force. A positive charge always in the direction of the arrows, tangentially to the field lines, and a negative charge in the opposite direction. How many field lines are there in space? Well, of course, there are an infinite number. Just like these little arrows that we had before, we only sprinkled in a few. But of course, in every single point, there is an electric field, and so you can put in an infinite number of field lines, and that would make this representation, of course, useless. So we always limit ourselves to a certain number. If you look very close to the -1, notice that all the field lines come in on the -1. We understand that, of course, because a positive charge would want to go to the -1. If you're very close to the plus, then they all go away from the plus, because they're being repelled. You can sort of think as these field lines, if you want to imagine the configuration, that the plus charges blow out air, like a hair dryer, and that the minus suck in air,